Today's background is Tokyo's best off-license. It's in a little suburb called Shimokitazawa, which is kind of a little bit like the new town of Tokyo. And the cool thing about it is, in addition to having really good beer selection, and that's stuff from all over the world, including some really exotic stuff that's very difficult to get, even in places like Europe and the US. The owners are also huge Star Wars fans, so the shop also doubles as a place where you can buy Star Wars kitsch, and it's kind of cool, even just to, if you're not a drinker, to just wander in and have a look around at all the really cool Star Wars stuff that they've collected over the years. The other nice thing about it is, when people think of Tokyo, they often think of concrete buildings and asphalt streets and not very much greenery. And this place is a couple of blocks away from one of the really nice greenbelt walks in Tokyo. And it kind of follows a little stream through the suburbs down to the Meguro River in Nakameguro. And so it's a really nice weekend walk if you're looking for something to do. Take the train out to Shimokitazawa, walk your way down to Nakameguro, and then take the train back in again. It's a really nice thing to do. I used to do it quite a lot. Okay, so where we're at, we're dealing with rotation of rigid bodies now, and we basically took a random rigid body. We defined a thing called the center of mass, which is where the mean position of the mass is, and then we basically set this up so that we can deal with linear momentum as just a motion of the whole mass acting at its center of mass, and we can then deal with angular components as a motion of the center of mass about some center of rotation, which is not necessarily at the center of mass. And we can also deal with a term, with a component that is basically the rotation of the object about its own center of mass. And the nice thing that turns up in this is that we can actually decouple those two motions. So we can treat the motion of the center of mass about some external rotation point as a separate set of motions to the rotation of the body around its own center of mass. And as we'll see later on, that actually makes the mathematics quite easy in various places. And so today's lecture, there's two more things I want to deal with. One is kinetic energy, and I want to pop out a nice little expression for what the kinetic energy looks like. And then the other thing that we have to deal with is start talking about moments of inertia. And you'll have done moments of inertia a little bit in first year, but now we're going to formalize them a bit more. Today we'll do them properly for rotation about one fixed axis. And then in the next lecture we'll start to generalize that even more so we can have more complex rotational motions than you will have dealt with in first year problems, where you pretty much always have an object with really good symmetry rotating about its axis of symmetry. Okay? So let's deal with kinetic energy. Kinetic energy for our particles is basically just going to be the sum of the kinetic energy of each of the little particles that we have. Okay, so we've got sum from alpha equals 1 to n of a half m alpha r dot alpha squared. Okay, where r dot alpha squared is just the square of the velocity. And again, we have this relationship that we had. I might jump back on that a slide just so that we've got the figure up. We've got r alpha equals big R plus r alpha dash, like so. Okay, so we can define every little mass in here either as its position away from an origin or its position away from the center of mass of the object. Okay. And of course, that little expression there, if we take the time derivative, r alpha dot is going to be big R dot plus r alpha dash dot. Okay, and I kind of used that implicitly in the last derivation, but there it is written out. Okay, so when we deal with kinetic energy, we have to deal with r alpha dot squared as the key functional term here. And so we can write that as r plus r alpha dash, and we should take the dots here, squared. And then of course we can multiply this thing out. So this is now going to be r dot squared plus r alpha dash dot squared plus 2 r dot r alpha dot dash. Okay, so it's square of the first, square of the second, plus 2 times the product of the two terms. And we can plug that now into our kinetic energy, right? So what we're going to have is a half, oops, hang on, I need my sum. Actually, I can put the half out the front. Half sum m alpha, and I can split the sum of the big sum of the terms into a sum of sums, right? So let's do these as individual ones. R dot squared plus a half sum m alpha r dot alpha dash squared plus sum m alpha r dot r dot dash. Okay, and on the end the half cancels out the 2, and that's why that's not there. Okay, now this final term on the end here is 0, and it ends up being 0 because we can write it as r dot sum m alpha r alpha dot dash, and we know from what we were doing before that sum over alpha of m alpha r alpha dash is just the position of the center of the mass relative to the center of mass, which is 0. And then if you take the derivative of 0, you get 0. Okay, so this thing is 0 in here, and so the whole term becomes 0. And what we're left with is just these two terms on the two ends there. Okay, so you can then write this thing looking a little bit like this, where we have a component that's connected to the motion of the center of the mass and the mass of the whole object, plus a term that's connected to the mass of all the little pieces and their positions relative to the center of mass. Okay, and so all we've really done here is, back when we were dealing with angular momentum, we looked at the motion of the center of mass relative to a rotating point and then the rotation of the object around its own center of mass. Now we're basically just taking a kinetic energy term connected to the orbital motion and a kinetic energy term connected to the rotational motion in that system. Okay, one of the joys of having a green screen and a green football, I guess. It's fun. Hopefully it's not freaking everyone out too much. Okay, so that's kinetic energy. It comes out quite easily. Similar piece of maths, right? And you can imagine that if the center of mass is not in motion, then we can basically just break this into a spinning component, right? So if you've got this spinning about its center of mass and there's no center of mass motion that you need to account for, then you can basically just treat an angular momentum that's connected to, a kinetic energy that's connected to that angular momentum of the spin component. Okay, and there will be a kinetic energy attached to that, right? If you want to make an object spin, you have to put energy into it, and if you stop it spinning, you can get energy back out of it. Okay, so there's kinetic energy connected to that motion. All right, the potential term is even easier. I'm not going to go into it in a lot of detail here. We can basically treat our object as a whole pile of internal potential energy terms, which is basically the attraction or repulsion between particles that make up that object. And that's kind of an internal potential energy connected to that object. And you can have an external one, right? And an external one would then be, for example, imagine that I make the whole thing positively charged and I put a negative charge over here somewhere. Then they might repel or attract, and then that's an external potential energy, right? We can make that up out of two components. And the external components really ends up acting on the as a center of mass type term. The internal potential energy is basically just the sum of all the particle pairs. Okay, and so if you then want to do Lagrangian style problems in there, you can work from knowing what the potential energy is and the kinetic energy is, and work into Lagrangian approaches. Okay, and we'll do maybe 1 or 2 Lagrangian problems in this sort of sense in the coming 2 lectures. We won't get to them today. Okay, and so now there's one last thing we need to deal with to do this properly, and that is to basically define how the angular momentum depends on the angular velocity of an object. And so the way we normally deal with this is to deal with something called a moment of inertia, okay? And so you'll have all seen this in your first G lectures. You'll have some expression that looks like L is equal to I omega, where you have axis through your object. You will have some angular velocity omega, and to get the angular momentum, what you do is you multiply this moment of inertia by the angular momentum, the angular frequency, and that gets you your angular momentum, okay? And in first year, you deal with really simple problems where you restrict yourself generally to the axis for rotation being through the center of mass of the object in most cases, and being parallel to the angular momentum, okay? And you can imagine getting situations where, for example, the natural axis of the object is not passing through the position that it's rotating about, okay? So you can imagine setting up a fixed point on the surface here, for example, and making it rotate about that. Then your angular momentum will not necessarily be parallel to your moment of inertia axis, okay? And that's something we have to deal with in this course, is more complicated motions than that, okay? Because in first year, you basically just treat angular momentum is the same thing as your axis of inertia, and you always deal with nice symmetric objects so that your symmetry behaves well, and you get really nice simple expressions for your moment of inertia, okay? But ultimately, what we want to do is be able to deal with rather more complicated rotations. And so you can imagine something like taking this football and putting an axis that points in this direction through it, you know, and making it rotate about that position, right? And that's a perfectly legitimate rotation. You can see, you know, it can basically execute that. It's not through any of the symmetry axes, right? So that's the dominant symmetry axis. You can imagine there's a symmetry axis here as well a little bit, so motion like that, it's like, you know, something funny, and we have to be able to deal with those kind of rotational motions, and we avoid them in first year just because the mathematical apparatus that's required is a little bit complicated, okay? So what we're going to do for the last part of this lecture is basically just build that up for rotation about a fixed axis, so that in next lecture we can do even more complicated cases of rotation, okay? All right, so when we've got a fixed axis, and this is where things can be kind of interesting in rotation, the axis can be that you're rotating about can be fixed in space, or it can be moving, and it can be moving linearly, or it can be changing angle, right? So you can imagine that this object's rotating like this, and then it starts doing a tumbling motion like follows, right? And so the axis of rotation is actually pointing this direction and tips as we go through the motion. So we need to be able to deal with cases like that. So when we have a fixed axis, so really simple case to start with, just some motion like this, what we can do is take that fixed axis and call it our z-axis, okay? And there's no reason why it has to be z, it could be x, it could be y, but normally by convention we call it z just to keep things nice and simple, okay? We have our angular momentum, and it's basically the sum over alpha of the angular momentum components of all the little pieces that make up that body, okay? And so we can write this as, just as we had before, R alpha cross M R alpha, actually let's make it V. V alpha, like so. And we know that our V alpha here is basically omega cross R, like so, okay? And you remember we got this in a lecture or so ago, and this is the one case where we have to put the R at the end to make this work properly, okay? So we have an angular momentum vector, and in this nice simple case where we're rotating about a fixed axis, we can make that vector point along Z. So what we can do here is basically write our omega vector as something that looks like 0, 0, and omega. Okay? And then our R alpha we can write as X alpha, Y alpha, and Z alpha. And we can then get our V alpha in here as omega cross R alpha. And we can do that just as a standard cross product in here, right? So this would be I, J, K, 0, 0, omega, X alpha, Y alpha, Z alpha, like so, okay? And then you can work through this. It's a standard determinant setup, so it's I and the two terms off to the side here, so it'd be this times this minus this times this. So that will get us minus, wrong color, minus omega y alpha in the I component. Let's just make that a y so it's clear. And then the middle one is j times, and we do the cross the other way around, so it's this times this minus this times this. So it's going to be omega x alpha in that direction. And then the k here is going to be this times this minus this times this. So what we're going to get in here is 0 times 0 is 0 on the end. Okay? All right, so that's that. And then, of course, we need our L alphas in here. So it's going to be M alpha, R alpha cross V alpha, which of course, you'll see this later on. We could write this as R alpha cross omega cross R alpha, right? In there. And so this will be, keep our M alpha at the front. We need to do another determinant in here. So I, J, K. We've got X alpha, Y alpha, Z alpha. And then the terms in the bottom here are minus omega Y alpha, omega X alpha, and 0. And so we can work this through. Same approach as before. So this is now going to be, if we take the I, it's going to be Y alpha times 0 minus Z alpha times omega X alpha. So this will be omega, sorry, I need a minus sign just here, minus omega X alpha Z alpha, comma, J is now going to be that term first, that one second. So this will be now minus omega Y alpha Z alpha. And then the last term here on the K is going to be omega X alpha squared minus Y times minus Y. So it's going to be plus omega Y alpha squared. Let's just slide this over a touch, just there, okay? And of course we can pull a term in omega out the front, so this is going to be M alpha omega, and we're going to have minus X alpha Z alpha minus Y alpha Z alpha and X alpha squared plus Y alpha squared, okay? All right, we can now get the total angular momentum, and we can start just with so our total angular momentum here is going to be basically an Lx, an Ly, and an Lz, right? 3 components. And so we can pull out those 3 components one by one. So let's pull out the first one, Lz. Lz is going to be sum over alpha, M alpha, omega, and then just the Z component for our total angular momentum above. And you'll notice that what I got here was the little individual components. The total angular momentum will just be sum over alpha of L alpha like this, right? So I just have to include a sum in here, and that's what's popping in up the front here, okay? So this is now going to be X alpha squared plus Y alpha squared, like so, okay? And you'll remember when we did this in the last lecture, we can define a row here that is basically square root of x squared plus y squared right? It's basically if you have, you know, some origin O and something rotating about that as your axis, then this distance from the axis out to that body here is rho, okay? And just so everyone's clear, when I write a P and a rho, a P will look like this, and a rho will have this little stroke through the middle of the P, if I'm handwriting them, just so you can interpret my notes. Okay, so basically that rho is just the distance from the, you know, if I've got an object rotating on its own axis, it's, rather than being the position from the center of the object out to that position, it's the distance from that position to just its nearest point on that axis. Okay. And so what we can do in here is write our Lz as sum over omega m omega rho alpha squared omega. Okay, and you'll notice that this thing we could write as I z omega, where Iz is sum alpha m alpha rho alpha squared. Okay, and this thing here is a first year result. Okay, you'll remember getting this in your first year physics courses. If you have a body that's, you know, symmetric in some way, then you can get the moment of inertia for it as the mass times the distance of the little piece of mass squared away from that axis, and then just add that up over the whole object, right? And then in some cases you will have done that as a integral as well. So basically all we got is just a first year result, and what this thing is called the moment of inertia. And we don't even need to refer to it necessarily as the z-axis there anymore, because it's really just the axis of rotation for that object, okay, because we're rotating about a fixed axis. Okay, and at this point I just want to take a brief diversion into kinetic energy. Our T is just a half sum of m alpha v alpha squared, and we know that v alpha is equal to the radius, or the, you know, if we've got something rotating about an axis, the distance out to that object from the axis times the angular frequency, right? So it's going to be rho alpha omega. And so we can substitute that in, so this will be now half m alpha rho alpha squared omega squared, okay? And then of course this term in here is just my Iz, so this would now be a half Iz omega squared, and you'll remember this is a result that you got in first year as well. Kinetic energy of a rotating object is just the moment of inertia times the square of the angular velocity. Okay, so far all we've really got out is first year answers out of this. And what we've done is, rather than first year be given this thing called the moment of inertia, what we've actually done is pulled it out from first principles, right? We've basically just taken our definition for angular momentum and worked out that this thing exists. The two things that are new here are Lx and Ly. And what we can do in here is come up with Lx, and Lx will basically be, we can get it the same way that we did above. What we do is take sum over alpha of m alpha, and then bring down this term from the top. And what we're going to do now is bring down this term, okay? So what we'll get down here as Lx will be sum over alpha to get big L, and the components of little l alpha. So it would be m alpha omega dot minus z alpha x alpha. And this dot just here is just a normal multiplication, right? It's not anything terribly complex. And of course, this thing then is minus sum over alpha, m alpha, x alpha, z alpha, omega. Okay, just cleaning it up a little bit. And we can do a similar thing for Ly. So Ly is now going to end up looking very similar. I'll let you take the intermediate step. It's going to be m alpha, y alpha, z alpha, omega. Okay. Now, one thing you'll notice here is that in general, those two sums do not equal 0. And the case where they don't end up being 0 is the case where you basically don't have much symmetry in your problem. Okay, so often the way that you make Lx and Ly go to 0 is that you basically bring your system to a nice symmetric situation, and then what basically happens is the Lx and Ly terms disappear and you only deal with the Lz terms, right? And this is why in your first year courses you will always deal with objects that kind of have a nice symmetry rotating about an axis that passes along that axis of symmetry. It's there basically to make sure that those Lx and Ly terms go to 0 so that you only have to deal with Lz, right? But if you start to break your symmetries in these problems, what tends to happen is that these two terms Lx and Ly are not 0, and so what you have is that you can have an L that has Lx, Ly, and Lz. So it doesn't point along Z. And you can have an omega now, which is basically 0, 0, and omega, as we said before, because we're spinning about a fixed axis and we define that as our z-axis. And now we're in a little bit of trouble here, because in first year we would write an expression that looks a little bit like this. And we don't necessarily have L parallel to omega in this situation where we break that symmetry, right? We can have an angular momentum vector that for a rotation about a z-axis, and we define that z-axis via the angular momentum, so which way the rotation is about, we can actually have an angular momentum that doesn't point along that axis, it points in some other direction because of that breaking of the symmetry, okay? And to give you a really good example of this, when you drive a car behaves really well, right? The wheel rolls along down the road and it rolls very, very happily on its own axis. If you put it out of balance, and one way to put it out of balance would be just to hang a mass off one side of the wheel. What will happen now is that you've broken the symmetry and there will be an Lx and an Ly component. And what it will have is now an angular momentum that's no longer pointing about that axis of rotation. And so what you get is like a skipping. And so those of you who own cars, if you have a look at the tire, you'll usually notice that there's a little lead mass hanging on the tire. And usually when you get your tires done, the shop that does the work on the tire will do what they call balancing the wheel. And what they basically do is take the wheel off, put it on a thing, spin it, watch it wobble, put the mass in the right place with the right amount of mass so that it cancels out that wobble and brings the wheel back into symmetry. It's like a little correcting mass. And if you have a look, you'll see it's like a little lead mass. Sometimes you'll see them lying on the street because they've fallen off a car. And as soon as you lose one of those, if you're driving, you'll notice that the car kind of in one of the wheels because it's running out of balance, okay? And this is this case where you've broken that rotational symmetry and now you've kicked L a little bit off I, and now the system's trying to compensate or react to that change, okay? And so in addition to the term that you'll have from first year, this moment of inertia, we now have two additional terms operating in the other two axes. So we often call these, because there's a z, because this term is a moment about the z rotational axis due to the z component. It's called IZZ. And then in here you can see there's a YZ term and a XZ term in here. So these are usually called XZ and YZ. Okay, these are the two things that you call the product of inertia, and they're basically the components of the inertia or the components of the angular momentum about the non-rotating direction for a rotation of something about a fixed axis. Okay. Okay. So in addition to moment of inertia, we now have two things we call products of inertia, and we'll see how they become really important in the next lecture. Okay. So just a quick finish off here. The x and y components of L are not generally zero, and that means that the relation that you learned in first year physics of basically L equals I omega as a vector relation is generally not true. Okay, so we do this a lot in physics. You're spotting that I'm sort of correcting a few of these both here and back when we did centrifugal force and a few other places where we kind of tell you, oh, you know, this thing holds. And we tell you that it holds because we don't want you to get completely hung up in complicated cases too early, because then life gets harder, right? So we restrict ourselves to really simple cases and keep it simple, and then we have to fix ourselves up later. And this is one of these cases, right? So in all of your first year problems, you'll be dealing with highly symmetric situation, rotation about an axis that passes through that symmetry axis, and Lx and Ly are zero, your products of inertia are zero, and so you get this really simple situation you learn in first year. When you're dealing with general rotation, that goes in the bin. So if you're not rotating about a symmetry axis, then you have to be a bit more careful. There's a little bit more going on in here that you have to think about, okay? All right, I think we might finish there. And next lecture, we'll deal with not just rotation about some fixed axis, but some rotation about axis that might be changing as a function of time, so that we can deal with even more complicated rotations as we go on through the subject. I'll see you next time.